In part 2, we'll review the principles behind performing load calculations and how they apply to system design. The learning outcomes for part 2 are to learn how heat transfer impacts comfort, to understand what a load calculation is, to learn the basics of performing a load calculation, to understand what affects the heating and cooling load of a home, to learn about different resources available to contractors, and to understand key considerations for performing an accurate load calculation.
And now we'll start part 2. In the process of heat transfer, there are 3 key principles that follow natural laws of physics. The first is often called the law of conservation of energy. This is that energy can neither be created nor destroyed. It changes form from, say, electrical energy to thermal energy, but the net amount of energy always remains the same. The second principle is that heat is transferred by means of conduction, convection, and radiation. Conduction and convection can be confused because their spelling only differs by a couple of letters. Conduction occurs through direct contact. So one way of keeping them straight is that conduction has a D for direct in its spelling. In the winter, heat escapes through the home's envelope. Warm inside air comes in direct contact with the inside wall and warms the wall by conduction. The heat travels through the wall by conduction, then through the insulation by conduction, then to the outside wall, and finally from the outside wall to the air outside, all by conduction. Natural convection can be thought of as heat moving within a fluid that moves because of differences in specific gravity or differences in pressure of the fluid's molecules. The simplest example of this is hot air rises. As a portion of the room's air is warmed, the distance between those molecules increases, making that air less dense and allowing it to be buoyed upward. Forced convection is when heat contained in a fluid is moved by mechanical means, such as when a fan moves air through a ducted air distribution system. Radiation, for HVAC purposes, can be thought of as heat moving through air by line of sight with little warming of the air. The heat travels to a surface where it's absorbed. This example illustrates how comfort is impacted by more than air temperature. When we surround ourselves with cold surfaces and objects, body heat is lost to those surfaces, making us feel cold. To achieve comfort in rooms that are heavily glazed or poorly insulated, higher air temperatures and more heat are usually required. Radiant heat loss and air movement should be considered when addressing customer comfort. In addition to dry bulb temperature, occupant comfort also depends on humidity, air movement, and radiant losses to cold surfaces, such as a window pane on a cold day. There are 2 different load calculations that are typically done: the heating load and the cooling load. The instantaneous heat load is the amount of heat needed at any given time to maintain a comfortable indoor environment. The heat lost through the building envelope must be replaced by an equal amount of heat supplied to the indoor space. A house can be thought of as a box with exterior walls, a roof, and a basement. The walls and roof have an insulation or R value that slows down the rate of heat loss to the outside air surrounding the house. Heat always flows from high concentration to low concentration, or thought of another way, from a higher temperature to a lower temperature. During the cold months, when the indoor space is kept warm, heat is flowing through the building envelope to the outdoors. The heating system has to be sized and designed to replace the heat that is escaping through the building envelope. Therefore, heat, or thermal energy, must be added to the air inside the house in order to maintain occupant comfort and favorable indoor environmental conditions. The peak heating load is based on the coldest day of the year for that house's location, but it's not the absolute coldest day of the year. The peak load calculation uses a temperature in the 99th percentile of coldest days of the year, or 90 times out of 100, what is the coldest day of the year? This is true for traditional systems also. The coldest hours are so frequent and short-term, the system can recover after those hours have passed. For the non-peak days of the year, which make up the majority of the heating days during the year, the heating system operates at part load. To calculate a home's annual heating load, binned weather data is used to determine how much heat is required to heat a home for an entire year. Load calculations can be performed for an entire house or various parts of the house. When a thermal load is calculated for an entire house, it is referred to as a, quote, block load calculation. Alternatively, loads can be calculated for a zone of the house or on a room-by-room basis. Each individual room is going to have a different heating requirement based on the size of the room, the R value of the exterior walls of the room, the quality and size of the windows and exterior doors, the air infiltration, the orientation of the house, solar gains, etc. These are some of the many factors that go into the calculation of heat load. The Air Conditioning Contractors of America, ACCA, is the author of a manual entitled Manual J that describes the procedure and equations that are used to calculate heating and cooling loads for single-family freestanding homes. Although the calculations can be performed manually, a software program is usually used in conjunction with Manual J to perform the calculations. The ACCA has a list of approved software programs, and only those programs meet ANSI standards and also many of the building codes in the United States. Many of the software programs that are approved by the ACCA include local weather data that designate the design outdoor air temperatures for heating and cooling used to perform the load calculation. The collection of data for a particular home that is used as an input value for the load modeling must be done carefully and completely in order for the program to calculate precise thermal loads. The rule of garbage in results in garbage out is applicable. If the inputs are incorrect, then the output will be incorrect. The square footage of the home is a factor that is an input to the load calculation, but the square footage of the exterior surfaces, another input value, has a greater impact on thermal load since much of the heat loss occurs there. Many of the attributes of a house are site-specific. Does the house have a foundation that's below grade or maybe above grade? The insulation that separates the conditioned space from the basement space? Or is the basement considered part of a conditioned space? The thermal envelope is all of the surfaces that are separating the indoor conditioned space from the outdoor space. We have to consider all the penetrations through the thermal envelope, the window locations, their size, their U value, their overhangs or shadings, are there blinds on the window that are reflecting some of the solar gain? The orientation of the house as a whole, how it aligns with the sun. How much exposure or seasonal shading does the building receive? Is the house on a clear-cut lot? Or do we have a shaded lot where the house has fairly large trees around it? That all affects the solar loads. To some degree, we have to consider the wind exposure. We also want to look at the structure of the roof, the venting and the insulation levels in the attic, and the total surface area of the attic space. Is it a cold attic with high R value between the conditioned space and the unconditioned space? Or do we have a vaulted ceiling where we have several inches of insulation before the roof that's being shone upon by the sun all day? Also, want to take a look, obviously, at the walls, the thickness of the insulation, the R value of the walls themselves. Does the wall cavity have insulation in it, or is it empty? If it's insulation in it, or just maybe thin batt, maybe 1 or 2 inches, or it's a full dense packed cellulose, or does the wall have continuous thermal envelope throughout the entire surface area? Does it have polyiso underneath the sheathing? And then what about the forced air ducts of the home? Are they located inside the conditioned space or outside the conditioned space? What's the quality of those ducts? Are they sealed tightly, or has the old duct tape dried and peeled and they've become leaky? If they're leaking into the conditioned space in the attic, that's all conditioned air that's being lost directly to the outside. Load calculations can be performed for the entire home, often called block load, or room by room, or by specific areas. These design considerations should be reviewed when determining how best to model the building. In all cases, it is significantly better to reduce the load first, then size the system. This can allow for smaller and less expensive heat pumps and ensure the system is not oversized for the home's actual need. This will also make it easier to match available heat pumps to the home's overall load and energy need across all conditions. A leaky, high-load house requires a larger heat pump to cover the peak heating need, which inevitably leads to an oversized heat pump for mild conditions. More on that dynamic later in the presentation. Climate data has to be linked to the home's location and used for heating and cooling load calculations. Heat pumps can be sized to serve a single load, multiple loads, or the whole house coverage. Backup heat refers to the secondary heating system designed to provide heating to the entire home in case the primary heat pump system is either out of service or unable to keep up with the current load. Supplemental heat refers to a secondary heating system designed to provide heating for a portion of the house not covered by the primary heat pump system. Here's a link to the ACCA website where their manuals for load calculation, equipment selection, air distribution, and duct design can be purchased. Also shown is the link for the listing of approved load calculation software. Although the process for performing heat load calculations and selecting equipment may seem challenging, it boils down to only 4 simple steps. 1, calculate the heating and cooling energy needed based on heat transfer principles. 2, determine the duct loss. And 3, determine the impact of infiltration. This will be expressed in air changes per hour. And lastly, select from a limited range of heat pump capacities that are available in the market. For ductless systems, we forego the duct loss calculation entirely and have a wider range of equipment capacities to choose from. Common capacities available are the 6,000 BTU per hour unit or a 12,000 BTU per hour unit. And then the sizes increase in increments of about 6,000 BTUs an hour, all the way from 18,000 up to 48,000. And then, as you can see, there's also available a large 60,000 BTU an hour heat pump available. Some states require manual J and S documentation for code compliance, but allow jurisdictions to grant local approval of alternate methods. Alternate methods and tools can be valuable or useful complements to manual J. Regardless of the tool used, load calculations provide the critical information required for proper heat pump selection and sizing. There are several well-developed, industry-vetted, and easy-to-follow recommended best practices available on the market. The Northeast Energy Efficiency Partnership, Minnesota Air Source Heat Pump Collaborative, and the Northwestern Energy Efficiency Alliance, we have heat pump manufacturers as well that all produce documents and guidance to help contractors design and select equipment correctly to ensure performance that homeowners expect. Here's an example of a very basic rule of thumb for estimating heat loads based on a few outdoor temperature conditions and construction types. Remember, rules of thumb are to be used only as a sanity check and not for actual load calculations. But you can just pick a typical value here, looking at a 2x4 construction with the double pane windows and a design temperature between 5 and 20 degrees Fahrenheit. The rule of thumb is that it takes about 19 BTUs per square foot of floor space to heat it. And that concludes part 2 using load calculations.
So in part 2, we learned how comfort is impacted by more than air temperature. Comfort also depends on humidity, air movement, and radiant losses to cold surfaces, such as a window pane on a cold day. We discussed load calculations, and that they're used to determine how much heat is being lost through the building envelope to the outdoors, and that many factors go into the calculation of the heating and cooling loads. We saw that ACCA's Manual J prescribes the procedure for calculating residential heating and cooling loads. We learned that a thorough takeoff is needed for accurate load calculations, the R value of the exterior walls, the quality and size of the windows and exterior doors, the air infiltration, the orientation of the house, solar gains, etc. These are some of the many factors that go into the load calculations. We learned about the resources for load calculations and that they can be found on the Air Conditioner Contractors of America website, which is acca.org, as well as the Northeast Energy Efficiency Partners, or NEEP, and others. And finally, we touched on the key considerations for accurate load calculations, including heat transfer through the envelope, losses through the distribution system, and infiltration losses, and use these factors to determine the loads and select the appropriate equipment.